from which we launch our cargo, whatever the cargo may be. The policies all say that that's doable. The laws also say it's doable. If you look at the law of the land, now you have too many problems with state actors. Okay? Somebody wants to do it our way, or somebody wants priority because it's my dirt that you're standing on. It's also easier to safeguard it if you're out in the middle of the ocean. So the law of the sea is much more forgiving than the law of the land. Law of the air, again, you have to be able to make some compensations for movement. Space law is a very new field. There are exactly, anybody have any idea how many space treaties there are? 7. Basically, it amounts to 1, but there are in fact 7. The one is the original, the 1967 Outer Space Treaty, as it's normally referred to. The Moon Treaty was an attempt by the United Nations, and by the way, the United States was very involved in it, to make the things you can get from space, be they mineral or scientific or anything else, the common property of mankind. Now there's a real problem with that. We have something called the profit motive. And if there is no profit, there is no motive. And if you don't have a profit motive to go after an asteroid, for instance, if you're going to mine it, because I then have to share it with everybody in this room, I'm a very generous person, but I'm not that generous. Because it takes billions of dollars to get that project out there, to bring back something that is of use to us. There is a UN treaty that says that the seabed is for the common use of mankind, which is probably why none of the magnesium nodules on the seafloor have ever been mined. Even though magnesium is a very useful, very under-available mineral. Okay? So we think that we're pretty much covered in all of the law of the sea, law of the air, law of space for putting up a space elevator as long as there is some mechanism to move it. You have to be able to get out of the way, unlike the Iridium satellite that was blown up by the old Russian rocket body a couple of years ago. Now we have even more lovely space debris because it couldn't get out of the, well, it could have if it really saw it was coming, but it didn't get out of the way. So that's why we've chosen this particular regime, using sea and space and air as our laws and policies versus using the law of the land. Simply easier and more open, much more open. Skip, you next.
Okay, Pete pointed out a couple things on this slide. Oh, pointing. Here I thought I was pointing. Okay, I got it. All right, so this is sitting out in the Eastern Pacific someplace, picked because it's a low lightning zone. We got stuff on the HQ and POC is the headquarters and primary operations center. Somewhere on land, we're saying it might be in some place like San Diego. We've got to get stuff from the place where we build them and operate them and buy them and everything else out to here, and we've got some ocean-going transport to do that. You'll notice several different renditions here of what a climber might look like. They all have several things in common. That is, they got to clamp on to the ribbon, carry a payload in themselves up to the higher altitudes. This is Cathy. I'm going the wrong way. Yeah. There. Okay. You can look at these things. I won't talk all of them in a lot of detail. This is your ocean-going transport here. These are real. The oil drilling platforms have to be serviced by these things. There's industries, fleets of these guys that take stuff from the land out to the platforms out in the various oceans. This is an existing kind of thing. Again, an oil derrick kind of thing. We don't think we're going to do helicopters very much. Number one, you'll see in a minute. I'll go ahead and talk to you here. It takes 5 days at 30 knots from San Diego to get to the Eastern Pacific where the oil well drillers would be. That's a long time. And a long distance, there's not many helicopters that can do it unless you carry a lot of extra fuel. So this will be for safety of life kind of things, or maybe emergency kind of parts that you don't want to wait 5 days for. And I think you can see everything else on there, and we'll go to the next slide. I'm only going to talk about a couple of these. The most common mission is going to be to take satellites to the geosynchronous altitude. That's what geo is, geosynchronous. There's a lot of money up there. They're very expensive now because it costs a whole lot of money to launch them. We think the price will come down tremendously, and you can get new technology upgrades. The typical life for a geosatellite now is 15 years. Expect that to come down. There may be some low altitude stuff that gets dropped, but remember, as Pete was talking about, when you get dropped off, you've got a velocity. Well, if you're dropped off below geo, you're at apogee up in orbit. And so if you're not high enough, it turns out you've got to be about 2/3 of the way up. Otherwise, you're going to bang into the Earth on the other side. So you've got to get up high enough to miss the Earth on the bottom side. And so we expect some LEO guys will want to take advantage of the elevator, but the predominant mission will be up to geo. Okay, we have on here, we know we're going to get things running into our ribbon tether. We're going to have to fix them, and that'll be one of the missions that they'll do. You can walk through the rest of those things. I should have started off by saying that the climber is just another satellite. We know how to fly satellites. Been doing it for years. Okay? And so I personally don't think the notion of a climber carrying 20 tons, the electric motor for that, we know how to do that. Cranes know how to do that. Instrumenting them like we do satellites is a very mature technology. How to get those grippers on there is going to be a challenge. That's for the technical guys. We in operations will fly something like this. There'll be operations back at San Diego, like we talked about. There'll be a small operations activity on the platform too. We envision that we will have communications from where we load our cargo onto the climber and all the way up to geo. We think that there'll be communications package on here, just like most geo satellites are communications satellites. So we'll be able to talk to the climber, see the climber the entire time it's climbing. We'll also be able to take stuff back to the satellite operations center, the cargo for the climbers, and then back to the headquarters where the real operations are happening. Read through these bullets on your own. Basically, it's going to be very, very similar to launching a satellite because it is a satellite. But we're going to feature constant contact with our primary operations center. Standard satellite design has trade-offs between automation and autonomy. You'll see that into our climber. There'll be safe modes just like satellites have. The first 30 kilometers is uncertain how we're going to get up there. There's a lot of atmosphere to go through, lightning and wind and rain and bad stuff in general. And we're studying how to do that, lots of options, but we know once we get to 30, we'll be above all that bad stuff. We can deploy solar arrays, which are coming up here. This is loading the climber here. There. This is a climber with the solar arrays as it might be climbing, and then here's how the solar array would be deployed. Easy technology to get solar arrays big enough to power the climber. Okay, I think that's the rest is for me.
Which way's forward? Okay, nobody stood up with any questions? Okay, we'll keep charging. It turns out that the operations, as Skip said, are basically straightforward. The legal and policy will be discussed forever. But we, on the other side of it, the engineers, think that it can be done. I believe it can be done. We also, in our 3 group here, believe that it's going to be commercial, not government, that does this, because there's a profit motive. So those types of things coming together set the stage that we should start designing. We should get going. Now, the book that we talked about earlier that's going to be published from the International Academy of Astronautics, and I'll show you the outline and all that, actually comes out with 2 answers. The optimistic answer is if carbon nanotubes are ready in time, we'll be able to have this operational by 2035. So that's like 20 years from now. You guys will be in mid-career. You'll be wanting to take a ride. Okay, I mean, that's at $500 a kilogram. How much do you weigh? Don't say that loud. But and it's in kilograms, 5 by 3.2 or whatever. But anyway, the point is that you can, go on these things at a reasonable rate. If the tether's a little later, one set of analysts say it'll be 2060 before it's ready. I don't like to be that pessimistic. But anyway, the real kicker is both groups believe that we can have a space elevator. So what does it look like? Holy schnookers, man. It's outside of our magnetic field. So what does that do? We've got environments we've got to really figure out. Well, and fly it in there, but electromagnetic aspect. Plus, that's rotating. So it's only outside the electromagnetic, part of the day. The rest of it's in the tail and all. So it's going to be changing magnetic fields all the time. So we're in an environment that's going to be exciting. Really good stuff. Us engineers love that stuff. Anyway, it turns out that originally the idea came back in the late 1800s. It wasn't related to the design we have now, but he was talking, Tsiolkovsky was talking about something that grew from the ground up. In addition, in 1960s, more ideas came along. Well, the one that's related to us now is Dr. Brad Edwards came up with, for NASA, NIAC study, which is their R&D shop. How am I going to do a space elevator in the near future? Because NASA in '98 came up and said we can do one in 300 years. And the reason they had 300 years is they were using superconducting super trains that weighed 5 bazillion pounds trying to go straight up. It didn't work. So Brad Edwards said, oh, well, we can do that. So he wrote a book, did a NIAC phase 1, phase 2, then wrote a commercial book. And he came out and said, we can do it. That's all dependent on the material. I've got 2 charts on material in a few minutes. But he said we can do it in the near future. So Brad Edwards set the stage in 2000 to 2003. The last 10 years, we've been improving his design, because we've had a whole bunch of people around the world looking at this. This is being studied all around the world. I don't know if anybody has been paid to study it, except for a group in Japan. They just did a massive study in Japan, and they came up with a design, a Japanese design. They presented it in September. This is Brad Edwards' idea. Everything we talked about so far, except he had a laser providing electricity, providing energy to the receiver at the bottom, and that converted to electricity, which provided your wheels going up. Okay, so this is Brad Edwards. This idea was the right answer for 10 years. And as you know, all physicists and engineers want to argue all the right answers all the time. So we had a study just started 4.5 years ago that's concluding, and our book's coming out. And we looked at Brad Edwards' idea, and we embraced him completely. He's had great ideas. Except that our design on the tethered carrier, the climber, is a little bit different. And we came up with an idea that we really didn't want to use lasers pointing up. Both Skip and I, and well, Cathy outranks both of us, but anyway, we were in the military working in space, and pointing lasers that are 8 or 9, 10 megabit or megawatts straight up. What does that sound like? That sounds like a weapon to me, but anyway. But that's what they're planning on doing, having one of those looking up at each satellite. So if you have 7 on the ribbon, then that's a lot of energy focused straight up. And those satellites up there have got Earth sensors looking down. Dangerous stuff. So our group came up with the idea that indeed, if you get your efficiencies of your solar arrays up to 50%, by the way, we're at 28 right now in space. I've seen 45% efficient in the laboratory, and there's a new concept out there at 70% efficient. I have no idea what that is. It's called quantum dots. I haven't figured it out yet. Yes?
Why would the solar array efficiency be a requirement if you can just make that bigger and cheaper?
Exactly right. You could do anything you want, but there's a mass, an efficiency, inertia, all kinds of issues. So the higher efficiency, the better.
Right. So is that an efficiency just like how we technically define efficiencies, or is what that really is getting at is a mass to energy efficiency? Because that seems like something that would be more relevant.
Usually in the space world, we talk about efficiency of the solar arrays, but we fully incorporate the mass issue. I mean, when we deal with it. If you talk to the Boeing guys in their laboratory in Malibu, anyway, they do a lot of that. And the guys in Albuquerque in the Air Force do a lot of that stuff. And you're perfectly correct. When we talk about a space issue, it's efficiency, flexibility, mass, everything, all tied together. But for our sizing of the event, we said 50% efficient, lightweight, and flexible, so you can fold them up, you get through the first 30 kilometers of the atmosphere. Unfold them at 30 kilometers. And we've got sizes and masses in our book. But you're perfectly correct. It's all tied together. It's not just a straight, put the solar cell on the top of your house, the percentage. Okay, so our answer in our book came out to be solar cells. I have no idea what the right answer is, okay? I'm an engineer. What happens is you make incremental progress, and when you get to the point somebody says, here's $5 billion, go do it, you get serious about the trade. At that point, we'll make a decision. Until then, we got a bunch of engineers making trade statements. We believe this one's going to work, but you know, we're a few years away from somebody giving us $5 billion. It would be nice. Okay, another alternative, and of course we're 20 years from operation, is where do we put the marine node? The concept Skip talked about was a floating platform that moved, so that Cathy's ribbon movement for the getting out of the way of live satellites would work. Another answer that Dr. John Knappman came up with and has proposed is a high stage one. Literally, he's going to put a platform at 50 kilometers up there. So going from 0 to 50, you just have a box and you raise it up in an earth elevator type thing. You get to the location up there, take it out of the box, fold out your solar arrays, stick it on the tether and go. And it's a platform up there that will hold 400 tons. We describe that in the book on how you get that, but it's basically taking rods, massive 2-foot long iron rods, shooting them straight up, having the momentum of the bullet go up like this. As it's curved over, it's tossed energy up all the way along the tube, so it's forcing it up. And it's a very interesting design. I would say that's like a little riskier approach. But you know, we're at a stage where we want to look at all these riskier approaches. But the advantage of that would be phenomenal. We could have a workstation 50 kilometers up. You guys, you know, you'd be mid-career professionals then. You could be the chief of the 50-kilometer platform. Have a crew doing that. Okay, I said I'd talk about the materials. There's two good pieces of information about the material. One is, when Brad Edwards did this study 10 years ago, he came up with one material that could do it, carbon nanotube. Since then, 2 other materials have surfaced that might work. So we can choose from 3 materials now. One is, you know, carbon is, I think, 14 on the periodic table. You guys ought to know that better than I do. And boron and nitride are the other 2 right next to it. Is that right? Anyway, the 2 elements next to carbon combined form a molecule that's just as strong as carbon nanotube. So that looks like it might work. That's a less mature technology, but the beauty of that material is it works superbly in a vacuum of space with the radiation environment. There's some people that argue carbon nanotubes might have some trouble with the radiation. We're still working those issues. But the idea is 1 meter wide, multiple strands, Each one of those strands would be considered a rope made up of a whole bunch of strings, made up of a whole bunch of long individual molecules, you know, a bunch of atoms strung together. So we would do something like this because they will be hit by small particles, space debris. So what we're going to do is just accept the hit by small stuff. Put a hole through it. Okay, so what? Have a little inspection. Climbers go up and put a little paste there and pick it up. So have repair robots go up and do that. So that's the design. Now, just to be completely honest on the whole thing, the original idea was straight up 1 meter wide. Turns out you need a 100 gigapascal type material to do that. We're showing in our report that we can get by with like 35 gigapascals, but it means you taper it in the sense of where the most stress is right up at the top of GEO. You know, it's hanging all that mass below it, so there's the most stress. You have to have a little more density in the material. So it'd be a tapered thing, but that's a detail we'll work on later. Okay, here's some latest quotes. We're going for 35 megayuries, which is basically gigapascals divided by the density of the material, which is 1.3 grams per centimeter cubed, or something like that. Anyway, it relates basically 35 to about 42 gigapascals, something like that. So it's about a third of what Brad Edwards was saying. We've had some yarns grown longer than 40 meters at 1.7. So we're like a factor of 30 short, something like that, 25 or so. 10 to 16 megayuries has been manufactured. It's showing that there's 60 megayuries has been recorded in small CNTs, and a 46 megayuri mechanical properties was shown in experimental results. This is all 2010, 2011, you know, this is showing that the material should be there. So this is the critical stuff. If we give the material, all the rest of it's certainly not trivial. But it's space stuff we've done before. We can make spacecraft at skip pennies there. Okay, I've mentioned this report 2 or 3 times, but there's an organization called the International Academy of Astronautics. It's 1,000, 1,200 elected members, seniors, space gurus, all the disciplines, all the way from policy to law, to engineers, to scientists, to whatever. We meet once a year at a big conference. Cathy and I have been members for years. They run studies. They've done a nuclear propulsion study. They've done solar power studies. They've done a lot of studies. This one is going to be published in November. Oh shoot, it's already November, isn't it? Anyway, yeah, it's going to be published this month. And so the Academy is going to publish this study, and that's the topic list. Essentially a more detailed look at the feasibility of space elevators, similar to what we're talking about here, but quite a lot of depth. We had 41 authors. Remember, all of them are senior gurus from around the world. We had Professor Key from Japan do the legal chapter. We've got financial perspectives. We've got ops perspective. Skip basically wrote that. Now, Cathy read every word at least 3 times, and I thank her for that. She translated engineering to English. It's a very hard job, very hard job. The conclusion is over here. It's been approved by the Board of Trustees, 350 pages. The electronic version out for less than $10. The hard copy would be less than $20. It's going to be a phenomenal deal. But the conclusion is that the space elevator seems feasible. And that's remarkable because we can then take stuff to GEO for $500 a kilogram versus $20,000 a kilogram. Think of any transportation business that reduces the price that much. Plus we'd be able to do it every day, 14 metric tons per day. Now that's just per elevator. In our plan, we have 7 space elevators set up in the first 10 years. Different companies owning each pair. One would go up, one would go up, and then alternate with stuff coming down. So you'd have pairs of elevators, each commercial corporation. Okay, now I'm going to switch and look like Michael Laine. Oh, wait a minute, I already look like Michael Laine, except he's a lot younger. We're both tall, good looking, but anyway, he couldn't make it. I'm going to show you a few charts on the lunar elevator. The difference between the space elevator on Earth and the lunar elevator is basically two parts. One is you could do it today. Okay, we joke that we can use dental floss. I mean, the stresses are not that great. But that's the key point, that we literally could do the space elevator today. The second point we all have to keep in mind is that there's a lot of mass to get up there to do something like that. And if we put the space elevator on the moon first, we're still spending $20,000 a stinking ton to get it off the surface of the Earth, to get it toward the moon. But if you could do it, it'd be a really neat idea, because you would have access to the ground. I mean, the terrain of the moon. And it would really be a neat concept. Here's this idea. Just to put this in perspective on distances. As the moon rotates only once per, 24 days, whatever that is, whatever the rotation is, it's not spinning very much. So that tension provided by the rotation isn't there. So you have to run it further out to get that rotation, to get the tension. So literally, for a space elevator on the moon, you've got to have 250,000 kilometers. 2.5 times the distance of an Earth space elevator. But the good news is we can do it with Kevlar today. We do not need any new fancy carbon nanotube material. So we can do that today. So what does it do if you have a space elevator there? Think of the design of your little rovers and stuff. You don't have to have any propulsion to slow it down, you know. Now the disadvantage is you got to go to one spot. But Jerome Pearson, who wrote the original paper on this, one of the inventors of the space elevator, wrote a paper on like 78 or so on the lunar elevator. He not only brought it down to a location underneath the equator of the moon, but then he ran cable cars all around the surface. So it's a combination of tether to the surface and then cable cars around. So literally he would set up an infrastructure on the moon versus a bunch of little rovers running around. So you could very easily do human cargo around. Yes?
What was that first you mentioned?
Jerome Pearson. He's the originator of the space elevator, one of the two guys I talked about. And he came up with the lunar elevator about 5-6 years after he did the space elevator. You can see his paper and everything on the web. It's there. Yes?
The question, so if you got a space elevator coming off the Earth and you got another one coming off the moon, at the tips of them, how far apart would they be?
Yes. I've never asked that question. I don't know. I'd have to look at that. I'm not exactly sure what the distance is.
Well, theoretically, 50,000 kilometers.
Pardon?
Theoretically, it'd be 50,000 kilometers because you got 100,000 kilometers from Earth up.
Yeah.
Theoretically, it would be 50,000. But of course,
Yeah.
they're moving from different places and at different rates.
And it's elliptical orbit and be changing all the time. But the point is that there have been a few papers on taking Earth elevator, tossing it out, and catching it at the other end. However, you know, both, as Cathy points out, you're in different inclinations. So your Earth elevator is going at the eclipse, or the Earth's equator, and the moon is elevated, whatever the, I forgot all my numbers, but anyway, it's elevated up. Yeah.
So the space elevator, so are you going to have like one space elevator on the Earth, one space elevator on the moon, and they're going to be like two different ones, or?
I would love to have a monopoly. It ain't gonna work, man. As soon as the first one gets built, they're gonna build the second, third, fourth, fifth one on the ground.
No.
And then on the surface of the moon, it depends on what it's gonna be. If it's gonna be a government program, they probably do one. If it's gonna be commercial mining, be more than one. Now there is a slight problem in that uses the Earth's gravity to a significant amount. So you might end up leaving from the surface of the moon and then curving around.
Is the tether going to be like just one big one from Earth to moon?
Oh no, no. You got the from
So
one
you're
to
gonna
the other.
place different elevators, crossing layers, match up everything?
No, they don't match up, they just toss.
These are really two separate projects for many different reasons. So if you want to launch something from the Earth, then you're talking about any of the, we hope, to 7 pairs of elevators around the equator of the Earth. Now, if you're, for instance, doing space-based solar power, then you want to launch at different places because you want to be able to have your space-based solar power point down to the Earth, to energy, to whatever point that particular sponsor is. For the moon, it's whether, are you mining on the moon? Living on the moon? What is it that you want to do? And that's going to determine both the space elevators and the lunar elevators, or elevator.
You're raising your hand up.
Earlier, you mentioned this is Kevlar, the lunar elevator?
The stress in the lunar elevator tether is not very high at all.
Yeah.
You can use almost anything.
Yeah, that's what I was going to say. I followed this work for some time, and I actually read for their magazine, and they said they believe that X-ray would be a better.
I didn't say better. There. Okay, you guys, you're students, okay? The one reality is everybody can do a paper. Everybody can write a book. When somebody hands you $5 billion and say, go build this system, then you get down and you say, ooh, which one's better? And it not only will be strength, it'll be price, manufacturability, deliverability. I mean, there's so many things that go into the decision on what material. The problem with the space elevator on the Earth is the strength requirement is beyond what we can do today for a long piece of material. That's why we're working in the laboratory. We're starting to get it out of the lab into the engineering, but we're not there yet. We're still in the lab. Yeah.
So how do you get 250,000 kilometers of Kevlar to move?
You have
The
to
space
use a
elevator off the
rocket.
Earth.
If you use Laine's approach, which is let's do the space elevator on the moon first, you use rocket, same way we do today. But I like the answer of, I did a paper with Cathy and I'm trying to think who else it was, but anyway, we did a paper on lunar, Earth, and Mars space elevators. All 3 are attractive. If you've read Mars, Red, Green, the trilogy, they talk about space elevators there. The point, I said the best one to do is lunar. But the point is, everything's trumped by the simple fact of $20,000 a pound of geo. If you're spending that much money on stinking mass to orbit, it's stupid. By the way, rockets are stupid. You can quote me on that. We don't have any other approach. So we're stuck with rockets. But they really are stupid. I mean, think about it. You use up 94% of the mass on the pad, throw it away. Every time. And that's really stupid. And then it's even, I like to use a parallel way. You buy a car from Japan, they get on the boat, run the boat over to LA, take the car off, take the transportation vehicle, take it out to Catalina and sink it for a scuba site. That's what we do with rockets today. It's stupid. Now, I would love to have teleportation or anti-gravity, anything like that. But we don't see that in the near future, so I grabbed hold of this one, and the 3 of us are charging ahead with this concept. We'll see how it works out, and whatever works. Anyway, this is a concept, and then these are some ideas about where you would let it go. You literally come up to each one of those points and drop something off, and then it can scurry up and down the elevator. You can release from this elevator and have, forward thrust toward Mars and stuff like that also. So there's different uses of this elevator as well as lifting off the surface or dropping on the surface of the moon. The rotation has value, so you can use that energy to toss things in different directions. Many people over the years have claimed that the best way to make space solar power is to go to the moon and mine the silica manufacture it there, and then send it to GEO. That's cheaper than launching from the surface of the Earth. That's stupid. I mean, let's be real. That really is stupid. Here's a better one, okay? The fusion guys, the ones that want to provide you power, very inexpensive, and have no real residual nuclear waste and stuff. Those guys need helium-3. The big one lesson on that, but they need helium-3. It's in the ocean. We could manufacture it from the ocean. But it is better and cheaper to go to the moon, mine it on the surface of the moon. The sun puts helium-3 on the top surface of the regolith. Mine the regolith, sort out the helium-3, compress it, bring it back to the surface of the Earth. It's cheaper to do that than to mine it from the ocean. That's stupid, too. We got to have a space elevator make all this work. Anyway, so there's all kinds of ways to make this work. Here's an idea that Michael has for the feather climber, and you can see the wheel interaction with the material. It turns out one of the real issues with Kevlar and carbon nanotubes is the friction. It is very, you got to design it to have more friction than it naturally does. And so you can have your wheels running like that to get the most friction. He proposes that we really shouldn't put it on the near side of the Earth. I mean, near side of the moon. We should put the first space elevator on the far side of the moon. Why is that? Why would you want to do that? Man, a lot more science. We haven't been there. Think about a astronomy location on the far side of the moon. Complete blackness. I mean, it really would provide a fantastic location for astronomy. It would really be neat. So there's a whole bunch of stuff. Once we have been there, so we got to go figure that out. See what that's like. So his proposal and his thing is, let's go with the far side. Okay, conclusion. We can do it today, and he claims that it's the cost of a discovery mission to go do it. I wasn't in on that study, but Michael has some really good ideas and has worked very well with this, and he had a really nice Kickstarter program last year at some goal, like, you remember what it was, like $20,000. He got 8,000. He got 100 and something. Yeah, he got a really great response on Kickstarter. And so he's been really doing this hard, trying to design this. Came up with some really neat ideas. Okay, so my summary is $500 a kilogram daily, 14 metric tons and that's payload, that's customer payload per day. And then in the book we talked about 7 space elevators, 3 different corporations owning those for competition. And if you think about that, that changes the space world.
Don't forget to add the fact that you don't have the shake, rattle, and roll at launch.
Oh yeah. We haven't even talked about the environment of the spacecraft, the ability to redesign the spacecraft completely. There's no stinking 60-foot long, 30 feet diameter period. There's no restriction. You can make it as big and awkward as you want, so long as you have the center of mass centered near the ribbon. So your flexibility and design of that. Besides, we won't even mention the stinking environmental problem of burning rockets. But anyway, we won't mention it.
What's the primary size of the
Size, literally, there's no limitation. We could design a climber with an open platform. The limitation on mass, which is probably what you're at, right? Okay. The limitation on mass has to do with the stress in the tether and the strength of the tether. And we do a bunch of mathematical equations and say, okay, a real quick one, Ben Shalif came up with what's called the feasibility condition of a space elevator. This is chapter 3. If you say it's a 30 metric ton tether, that means it can hang a 30-ton mass at the bottom. So, by definition, that's a stress level that's acceptable. We talked about a 1.4 safety factor, so put all those numbers in. If you have a 30 metric ton tether, then you can climb with 20 metric ton climbers, let's say the 26 structure, 14 payload. Once you get up radius of the Earth altitude, the gravity makes it only 1/4 the weight. So it's 20 at the bottom, 5 here. You go up further, it's less. Literally, when you add up a bunch of them, spread them out right, you put 7 tethered climbers on a 30 metric ton tether at a time, one per day. It's a mathematical relationship between mass of the tethers, gravitational pull, and the strength of the material.
So if it was probably material, so is that the limiting factor, or is there something?
Yes, the limiting factor. Right now, I'll be honest, our design for the first one is robotic. I believe 10 years later we'll have humans. And we'll be going faster. And instead of a 30 metric ton tether, we'll have 100 metric ton tether. We'll have 500 metric ton tether. This is just the start. I see no reason why you can't run 4 of them together and have 4 times capability. I mean, there's so many things. What we're talking about is the first step, non-human, etc. And the basic driver for non-human is radiation. Yeah.
So what happens if it breaks?
Very good question.
When it
It's probably going to break, but okay.
It must. Everything does.
Wait,
So
okay.
part of Peter
Okay.
talked at the beginning. Can you go back to that chart? You will have blow-throughs, as we call it.
Oh, the material.
And space debris can be a dust particle. It can be the camera that fell out of, the Apollo. It can be any number of things, or it can be a huge rocket body, such as the one that hit the Iridium satellite. For the big things, you can and must move out of the way. The question is, how many, and Skip is really our guru on this, how many and of what size can you absorb over what period of time? Did we do a backup chart on that?
Oh, yeah, but that's hard to get to.
Okay. At any rate, that says, Skip, how many, it's once every 10 years?
How many what?
How many hits above the blow-through size that you'll get on a space elevator?
I think you said 1 every 3 or 4 weeks.
Well, you're going to have one every 3 or 4 weeks, but the bigger than the blow-through ones. So the real answer is, for the big stuff, you see it coming, you move out of the way.
I mean, I'm just curious. So let's say that someone decides to be a jerk and destroy a marine station. Would it coil around the Earth?
No.
Okay.
Would it fly?
It'll go flying off in space.
Okay,
You ever
well,
play Crack the Whip?
Okay,
You ever play Crack the Whip as a kid? So you've got a bunch of kids roller skating or ice skating or whatever, and as soon as you let go of that kid on the end of it, he goes hopefully into the hay bale or the snow drift. Otherwise, it's into the brick wall, and it's not fun. And how do you explain that to your mother?
There are 2 groups of people right now studying that. Paul Williams in Australia, Professor Paul Williams, and a movement, I think her name is, in Spain. And they're looking at that very heavily. Paul Williams turned in 150 pages for our book on STEM. Of course, it had 500 images. But anyway, we cut it down to 6 pages. The bottom line is that if it breaks above, say, 3,000 or 4,000 kilometers, the upper portion is going to go out in that direction. The lower portion is going to fall in. It turns out if you do it at 10 or 12,000, then that's 10 or 12,000 kilometers, but it is not going to wrap around. It's going to fall down and trail behind. The atmosphere is going to pull it together and something, and it'll be a very light material. Now, if you have a climber there, it's going to provide some real energy coming down and things like that. But, the studies showed that the dynamics are such that if you cut it too high, you're going to lose the whole thing. And there are all kinds of dire concerns about it. My answer as an editor was, we'll show one of those cases, which we did. And then we'll show the logical one, which is the space station runs into it, or a large piece runs into it at 800 kilometers, 400 kilometers up. clamp the material at Geo, and the guy at Apex Anchor, the reason I call it Apex Anchor versus Brad Edwards, who called it counterweight, is I believe the Apex Anchor's got to have thrust. It's got to have a computer, it's got to have communication, so that it can thrust down and make up for that, and then you deploy something. So I believe that sever in a bad place would be total loss. Sever in the lower portion, say below 2,000 kilometers, I believe you can recover from it if you plan on your system engineering design from the beginning to like clamp it at Geo with a massive body there and have a thruster on the apex anchor, and you could stop the motion. And then you just let it down just like you deployed it earlier. Those have to be steady. Those are not definitive answers. We do not have any definitive answers on the sever issue. We've got a lot of work to be done there. And I think the worry is that people automatically jump to the answer that it's going to sever. If I were a bridge builder, everybody said it's going to fall down. Okay? Not going to fall down on my watch. I'm going to build that sucker so it works. Okay? I build rockets so they work. Every once in a while they blow up though. You know? So you got to plan for the downside, but you want to work it so that it's not going to break at my watch. When I sign the design sheet as an engineer, I'm saying it's not going to break.
But you're skipping the point. I'm going to wait for you to say it. The very first thing you do after you build a space elevator is build a section.
Skip has had this point for 5 years, and he's perfectly right.
And you decide how many you have to have as a minimum, and when you hit the minimum, it's called resupply level in logistics. When you hit that one, you build another one. You make it so you never have to launch with rockets again.
Right. Let me get to the end here real quick, and then we'll open up summary. I love, these are good quotes, but I love the one in the middle that says, the dinosaurs became extinct because they didn't have a space program. Now you think about that a little bit, we can take it to the next stage. If we don't have some way to get people off the planet of the Earth, you know, humanity's at risk for a while. So these are some neat quotes in the sense that we need to do these things. A guy on BBC was doing the 20 predictions for the next 100 years, and he included the space elevator. So, you know, it's on a lot of people's top. We belong to ISIC. I'm the president, he's the vice president. We just voted on that flip coin, but anyway. The point is we have a conference every year, August. The goals are to be the technical lead, you know, if guys have questions or anything. So www.isic.org. Come on over and join us. Reasons to join us. I told Mr. David Leonard. Great pickup lines at the cocktail party. But the bottom line is you'll really be furthering space exploration if you join. And by the way, we've got great student rates. Talk to Skip, he's a membership chair.
Yeah, we're going to have flyers out.
Yeah, we'll have flyers, and we'll have some tomorrow. This is the end chart, but I love what George Whiteside said. He was the Executive Secretary for National Space Society, and now he's the president or something of Virgin Galactic. So he's a player in commercial space. He talked at our conference, a few years ago, whatever that was, 04. And he said, until you build an infrastructure, you're not serious. Well, I claim we're not serious about space. Rockets are stupid. They didn't quote me on that. Rockets are stupid. They're not really an infrastructure. They're an individual event 85 times a year. We need to have an infrastructure. Teleportation's my best answer, but we haven't gotten there yet. We have to work on that. But space elevators really have a really neat answer. Okay, we're open for questions.
Yeah, so we've got just a few minutes here real quick. However, this is the last talk in here for the day. So I invite you all to come down, check out the books that they have, browse through them, and move the conversation on into the evening if you're so inclined to do so.
We're willing to stay a few minutes afterwards. There's no sweat. Do we have any questions for the next few minutes? Yeah.
You talked a lot about dropping off satellites. Did you theoretically pick them up as well? Like if there
yes, definitely. Yeah, in space stuff, Delta V works opposite. It's the same thing. It's all the same. Yeah, in fact, Skip talks about bringing back stuff all the time and bringing, one thing he says, we'll pick up debris and bring it down and then dump it in an orbit that for sure will go into the atmosphere so you don't even have to bring it all the way down. On the other hand, Skip keeps talking and reminding me about all these engineering problems. Think about it. We're coming down with a heavy mass. What do we need most of? Brakes. Oh, bummer, man. Not only do we need brakes, but we got to get rid of that heat. The heat issue will be tremendous coming down. So we got to get rid of that energy through brake into heat and reject heat. It's not a trivial problem in space when you don't have any air molecules to move the heat. You got to radiate it. So yeah, we'll bring stuff back all the time. Any other questions? Cathy, ready to answer any policy or legal? Yes.
Now, earlier you mentioned avoiding large objects that would potentially sever the nodes and the line. Moving those objects down on Earth, moving the base, you'd have to move quite a distance to make the part in outer space avoiding the object. You'd have to move quite a large distance. How would you keep that from swinging and pulling back into the Earth?
Okay, first off, the vector of tension is out that way. Okay, so it's going to be pulling that way. If we release it, the whole thing goes that way. So that we'll make sure we have enough mass at the apex anchor that that's true. Then what you do is you just, give it a jerk this way. So that's a velocity as well as a distance. And then it sets up a mode. Now, one of the things we're working on right now, we've got a research committee. We're trying to come up with a list of research topics that masters and PhD students or, seniors in college could get into and answer some issues, do a thesis on. And so those types of questions about what are the dynamics of the tether with different amounts of tether climbers on it, solar effects, lunar effects, right now that's being really pushed. There are 2 universities that are big time in that. McGill in Canada and Professor Fuji in Japan. I've forgotten which university that is, but he's really big time in that. So the dynamics of the tether are very interesting, and you would have to put up and make the dynamics, make it move out of the way of big objects. Now, the beauty is there are only so many big objects. There's a lot of little ones, but there is only so many big ones. And we've got all the numbers in our report on space debris.
In addition to moving the platform, you can also reel out a little bit. You can get just a few kilometers reeling out and get you several kilometers of movement so you can avoid the orbiting object.
The bottom of the space elevator is analogous to the kid at the middle of the crack the whip, and that's moving just a little bit to get all of that movement up there. But if I have a wish list, my number one wish would be for somebody to come up with a paper on that oscillation that happens and how you dampen it out the most efficiently. Because that is, in fact, the big question. You can avoid things. Okay, now what happens? What happens with the oscillation of the tether, and how do you dampen it out and retain as much as possible your straight line?
We just had our second meeting on the research committee, and the research committee identified that as one of the 2 big questions. So we started defining what do we need to know there, so that a researcher could then take our questions and put them forward into a thesis or a paper or a dissertation or whatever, postdoc or something. There's all kinds of stuff, but we're trying to do that in all the areas, including law and policy. George Washington University has their space policy. They could help us a lot there. There are some neat questions in the policy and the law areas that could be, a good thesis or dissertation area. This is an up-and-coming field with more questions than answers. Now, let me give you one piece of advice. One of the nice things to be is the world's expert. This is a perfect area, guys. There's only about 70 or 80 of us working in the field. Now, you can probably find a topic that's not being looked at. And by definition, you'll be the only one looking at it. And if you look at that, that makes you the world expert. I mean, nobody can argue that because you are the only one working it. Now, your thesis advisor would probably argue, maybe he knows more than you do. But anyway, if you study it long enough, you'll know more than he or she. Okay, any other questions? I mean, this is a neat topic with a future guest.
Yeah, I got a couple of questions, and I look forward to reading your book and getting a lot of those questions answered. But one question I had was maybe I missed it or something. You talked about the tether climber being mostly solar powered once you reached, what was it, 30 or?
Okay,
atmosphere.
Yeah, we want to get out of the atmosphere. We still have an argument between Skip, me, and John Hampton about 30, 40, or 50, but someplace in there.
So getting up to there though, it's not going to be, is it going to be solar still?
No, we're probably, Skip came up with the idea of a cable. You know, these carbon nanotubes are supposed to be phenomenal conductors and very, very light. So if we have a carbon nanotube extension cord, that would work.
30 kilometers weighs 15 pounds.
Yeah, I mean, we're talking about a phenomenal change in thinking, not only on the space elevator cable, but all the other aspects, the structure, the battery, the cable, power cable, stuff like that. We've got all kinds of options. But we have 3 options for getting to 30 kilometers right now. We have spring forward, which I think is hilarious. But anyway, you grab the cable and you bring it down, so it adds more tension to it. You bolt your tether climber on and you let go and it brings up. I mean, how hard is that, man? We're working on that one now. That's a question on dynamics and everything. The other is a cable like Skip is talking to, and then the third option is literally using a laser to provide energy, but only for the first 30 kilometers. Make it a small laser, not so big, that provides the energy. So you don't need a huge 8 or 10 megabit laser. Megawatt laser. You just need a smaller one. So there are different ways to do it. We're still, as I said, we're a long way from somebody paying me $5 billion to go build it. So there are a lot of questions.
You have the check.
Yeah, we'll take it. There's no problem about it. Anybody got a $5 billion sweet daddy or something? I don't know. We need some money. Anybody else?
Yeah, real quick. These are really sensitive. So, 2 parts. You said that these carbon fiber nanotubes were excellent conductors. So why wouldn't the tether be the perfect extension cord to provide electrical energy?
Yes. I've been asking that same stinking question for 3 years now. And I just had a gentleman named Dennis Wright, who's working at Lawrence Livermore, who does theoretical electrodynamics and electromagnetics in space and has a big code that he runs for the National Laboratory. And I met him down at the National Space Society conference in May down in San Diego and asked him this question. He got turned on, man. He really got turned on. He sent me 42, 50 emails, and so he came up in August and explained the electromagnetic effects of changing environment on our tether, and the answer came out no flippant way. He's the expert, but okay, you had a second part?
Yeah, the other thought was we're talking heat dissipation for braking, and what we use in automobiles now for electric hybrids is basically little electrical generators that do reverse polarity for regenerative braking. So why not just use batteries in our lifting mechanism, and as it comes back down, use the gravitational force, energize those motors, cause braking action that recharges the batteries as you descend back through the atmosphere.
Amen.
Yeah, I believe that's a very good idea until the battery blows up with too much energy. But no, I'm just saying that it's an extremely difficult problem. There are many solutions, and I don't know the answers.
But we agree that what you want to do is end up harvesting the energy that you create.
Yeah, I mean, otherwise it's entirely too wasteful, and ceramic brake pads just aren't going to cut it.
Yeah,
So,
we agree.
Particularly when you start deorbiting it, we're back to Skip's problem.
Now that's an area for you to become the world's expert.
There you go.
Right there, man. You can be the world's expert.
All right, well, let's thank our speakers.